Interconnected power systems come in various forms, each designed to address specific operational, geographic, and energy resource needs. National grid systems are large-scale networks within a single country, offering centralized management for electricity generation, transmission, and distribution. These systems are highly coordinated for balancing supply and demand, with the United Kingdom and the U.S. Eastern Interconnection serving as prominent examples. Regional interconnected systems connect several countries or regions, allowing for the sharing of electricity resources and enhancing grid reliability. Such systems are focused on load balancing and facilitating inter-area power exchanges. Examples include the European Power System, which connects countries across Europe, and the Nord Pool grid serving Scandinavia and parts of the Baltics. For broader cooperation, cross-border international grids link grids across multiple nations, enabling energy trading and providing support during emergencies. These grids are complex due to varying national regulations but are crucial for ensuring system stability. The interconnected grids between the US and Canada, as well as within Europe e.g., France, Spain, highlight this model. Microgrids, smaller localized grids, can operate autonomously or be tied to larger systems. They are commonly used in isolated regions, such as university campuses or military bases, to ensure resilience, especially when grid access is limited. Supergrids take this further by utilizing high-voltage transmission to link vast regions or continents, often aiming to integrate renewable energy sources. The Desertec initiative, which connects North Africa to Europe, is an example of a supergrid. Hybrid grids combine elements of both centralized and decentralized energy systems, integrating large interconnected grids with local microgrids or off-grid solutions. They are designed to facilitate renewable energy integration at various levels, such as in smart grid systems in the US or remote regions relying on both grid and renewable energy. Isolated standalone grids operate independently without any interconnection to other systems. These grids are often found in remote or island locations and rely on limited capacity, sometimes utilizing renewable sources like solar or wind. Islands in the Pacific or remote mining operations are typical examples of such systems. Each type of interconnected power system serves distinct purposes but collectively helps enhance grid resilience, optimize energy use, and support the integration of renewable energy sources. Operating interconnected power systems presents numerous challenges due to their complexity, scale, and the need for coordination among various entities. Here's an in-depth explanation of some key challenges in the operation of interconnected power systems. System stability and frequency control. Frequency stability. Power systems must maintain a constant frequency, e.g., 50 Hz or 60 Hz. If generation and demand are not perfectly balanced, frequency deviations occur, which can destabilize the system. In interconnected systems, a small frequency change in one region can affect others, making it challenging to maintain stability across large areas. Voltage stability. The voltage levels need to be maintained within permissible limits to ensure the reliable operation of electrical equipment. Interconnected grids are more vulnerable to voltage collapse, particularly under stress conditions like sudden demand surges or faults. Angle stability. This refers to the ability of synchronous generators in the grid to maintain synchronism. Large disturbances can lead to loss of synchronism between regions, leading to blackouts or cascading failures. Coordination between multiple control areas, independent system operators, ISOs, and regional coordination. Interconnected power systems are usually divided into control areas, each managed by different operators. These operators must coordinate the dispatch of generation, control of voltage, and management of transmission resources. Any miscommunication or lack of coordination can lead to issues like frequency fluctuations or instability. Inter-area power exchanges. When power is exchanged between different areas, the schedules must be followed rigorously to avoid congestion or overloading of transmission lines. Moreover, variations in power demand or generation in one area can have immediate effects on others, making coordination essential. Cross-border challenges. For grids that span multiple countries like in Europe or parts of North America, regulatory, legal, and political challenges complicate operations. Different countries may have different operating standards, environmental regulations, and market structures. Transmission network congestion. Overloading of transmission lines. Interconnected grids often experience congestion due to limited transmission capacity, particularly in high-demand corridors. This requires real-time management and redispatching of generation to prevent line overloads, which can lead to tripping or cascading outages. Optimal power flow OPF challenges. Managing power flows in an interconnected grid is complex, especially when dealing with changing generation patterns like variable renewable energy sources. The goal is to optimize power flow while avoiding congestion and ensuring all constraints thermal limits, voltage limits are respected. Loop flows, unintended power flows, known as loop flows, occur when power takes an unintended path through neighboring systems due to the interconnected nature of the grid. This can cause overloads in parts of the network far from the original source of the power flow. Renewable energy integration, variability and uncertainty. Renewable energy sources like wind and solar are highly variable and less predictable than conventional generation. As renewable penetration increases, balancing supply and demand becomes more challenging due to the unpredictable nature of renewable generation. Flexibility needs. A higher penetration of renewables demands more flexible resources, such as energy storage or fast-ramping generation, to balance the variability and maintain system stability. Interconnected systems may need to share these resources across regions. Impact on conventional generation. The rise of renewables has led to reduced operational hours for conventional power plants, particularly those with high fuel costs like gas or coal. This reduces their economic viability, even though they are still needed for grid stability. Cybersecurity and physical security. Vulnerabilities to cyber attacks. Modern interconnected power systems rely heavily on digital infrastructure and communication systems like SCADA systems for monitoring and control. This makes them susceptible to cyber attacks, which could disrupt operations, cause blackouts, or damage critical infrastructure. Physical security risks. Critical infrastructure like substations, transmission lines, and power plants are vulnerable to physical attacks, terrorism, vandalism, natural disasters. In an interconnected system, damage to key assets can have far-reaching consequences across regions. Power quality issues. Harmonics, power electronics and renewable energy sources introduce harmonics into the grid, which can affect power quality and damage sensitive equipment. Voltage sag. Swells and flicker. Rapid changes in load or generation like a wind farm suddenly coming online or offline can cause short-term voltage variations, affecting sensitive equipment. Reactive power management. Maintaining the balance of reactive power is crucial for voltage control. In large interconnected grids, managing reactive power can become complex, particularly during peak demand periods or in areas with heavy renewable penetration. Blackouts and restoration challenges. Cascading failures. Interconnected systems are prone to cascading failures, where an initial fault leads to a series of subsequent failures, potentially causing widespread blackouts. Events like the 2003 Northeast blackout in North America show the challenges of managing interconnected grids under stress. System restoration. Following a blackout, restoring power in an interconnected system is highly complex.